Hey, welcome back. And this is college algebra. We're into section 1.2, working with functions and their graphs. Okay, so let's get started. 1.2, basics of functions. Okay, so we begin with this idea called a relation, which is just a way of talking about ordered pairs. A relation in particular is just any set of ordered pairs. Okay. In these ordered pairs, there's two characteristics we can quickly define, and that's the domain and range. The domain are the first coordinates, the x values, and then the range are the second coordinates, the y values. Okay. So, for example, let's take a look here. 2, 1, 3, 2, 4. And then 3, 3. Okay. So that thing there I just wrote is a relation. We can literally graph it in the Cartesian coordinate system. Another way of visualizing these things is using arrow diagrams. So we're going to put all of the domain elements on the left. So we have 1, 2, 3. And then all the range elements on the right. 2, 3, 4. Okay. And if they're connected by an ordered pair, this is the domain, this is the range. If they're connected by an ordered pair, we're going to draw an arrow. Okay, so 1 goes to 2, and 1 goes to 3, and 2 goes to 4, and then 3 goes to 3. Okay. So there is a representation of a relation. We're interested, we try to classify all these different relations, okay? And that makes life a lot easier for us. It allows us to kind of identify patterns, and maybe if you have a certain relation, it follows this kind of format, and then you can identify shortcuts and all this other great stuff. So the first kind of characterization of a relation is this thing called a function. And a function is where every item in the domain goes to one and only one item in the range. Okay? So in particular, the relation I just drew is not a function because that element 1 in the domain goes to 2 different elements in the range. So because of that, this is not a function. In the set notation, you can tell because that 1 is a repeated element. This here and here. In the set with the ordered pairs, you see that thing I just underlined in blue? That's bad news for function-wise. It's still a relation, that's fine, that doesn't change, but it's not a function. So we need a definition for function, right? So what the heck is a function? A function is a relation where each member of the domain, or each x value, corresponds to exactly one y value. Okay, so I don't know, another example. Let's do the relation 5, 6, 5, 7, 6, 6, and 6, 7. Okay. So already, if you're kind of paying attention, you know it's not a function, right? Because the 5 is repeated here. But not only that, the 6 is repeated here. Let's take a look and see what it looks like. So we have 5, 6, and then we have 6 and 7. So 5 goes to 6, 5 goes to 7, 6 goes to 6, and then 6 goes to 7. Okay, so again, there's this splitting that happens in the domain. You don't want that, so it's not a function. Okay, let's look at another example. 2, 1, 3, 1, 4, 5, and then 5, 1. Okay. So the domain elements 2, 3, 4, 5. The range elements 1 and 5. So 2 goes to 1, 3 goes to 1, 4 goes to 5, and then 5 also goes to 1. Okay, so when you're doing this, you're only looking at the domain. Okay, in the range, you have a bunch of things going to one thing. That's fine. That doesn't mean it's not a function. The only things you're really looking at are the domain elements. Okay, 2, 3, 4, 5, and so long as you don't see any of that splitting happening, you're fine. So this is a function, even though it may look like, okay, in the range there's some issues, some weird issues, right? That will affect its invertibility. Okay, we don't have to worry about this otherwise, though. Oh, great! This stupid thing is popping up again. Okay. Let's now carry on to functions as equations. Right, so usually you can kind of tell whether a function is an equation by solving for y. Okay. As long as you don't end up with a plus or minus issue, you're good to go. Okay. So what do I mean by that? Let's look at let's look at this example. Okay. X squared plus y squared equals 25. This is actually the equation of a circle. Let's go ahead and solve for y. Okay, so y squared, I'm going to move the x squared over. And then I take the square root property. So y is plus or minus the square root of 25 minus x squared. This is bad news. As soon as I see that plus minus thing pop up, it's not a function. Because for for most of the x values, you're going to end up with 2 different y values popping out. Okay, so in particular, you can even try one. Let's say x is equal to 3. Okay. In that case, y will be equal to plus or minus square root of 25 minus 9, which is plus or minus square root of 16, which is plus or minus 4. In other words, you had 2 ordered pairs with the same x coordinate. This tells me I have 3, 4, and 3, negative 4. And so you have that repeated x value going to 2 different y values. It's not a function. Okay, so long story short, when you're solving for the y value, or for what they call sometimes an explicit formula, if you end up with a plus or minus, it's not a function. Okay. Otherwise, you can kind of bet that you're going to be all right. In those cases, no, not a function. Okay. So for something like an absolute value version, you're usually okay. Absolute value of x minus y is 5. So add y to the other side, subtract 5, and this is a function. Okay, let's carry on to functional notation. And you could literally think of functions as things that transform the shape of something. So it's literally, you're putting something into a machine and it's changing the shape of it. The way we usually think of it is kind of like a point-wise deal. So for example, you have a function f of x equals 3x plus 1. Okay? So as a machine, usually the way we do it in our classes, we think, okay, I'm just going to put in one number and see what happens, like 5. I'm going to put 5 in here, okay, into our machine f. And then an output will be this other number, f of 5, which in our case is 16. Right? I just plug 5 into f of x. Okay, so that doesn't quite seem like you're changing shape. You're going from one number. I guess it changes the shape of the point, the number there, but it's not really. We don't think of it as changing, something, but it really is, and it's a crazy thing, and you can experiment with it, and it's fun. It's a machine. It's a machine that exists in this invisible universe called mathematics that you can study and see what happens. And yeah, so that's what I mean by point-wise. We kind of look at the points and watch how they get changed. Later, when we work with domain and range, later in this section, we're not just dealing with points. We're dealing with whole intervals. And then when we graph things, we're kind of looking at how that number line has been kind of changed. It's a transformation. It's really like working with clay. You put some clay in there and you shape, the artist shapes it into some other form, and that's the output. So it seems like it's really abstract, and it's kind of, this is kind of a bunch of baloney. But no, it's really at the people study that kind of stuff, it's important. So anyways, there's our function machine. The thing going in on the left-hand side is called the input. They also call it, the independent variable. The thing coming on the outside is the output, which is dependent on the input, so it's the dependent variable. And usually we don't think in terms of some particular value. It's, instead of 5, it's just some generic x. And then over here, it'll be f of x. Okay. Let's work with doing some evaluations. Okay, so, for example, we have a linear function, 3x plus 7. And I want to evaluate f of 4. So how do I do that? Well, you're plugging 4 into this machine, and it's changing its shape, right? 12 plus 7 is 19. So wherever I see x, I'm going to put parentheses 4. And okay, let's try another one. You don't just have to put numbers in there. You can put in other algebraic expressions, right? So like x plus 1. So wherever I see x, I'm going to replace it with x plus 1. It totally changes the shape of the x plus 1 into something else. So now it's distribute the 3, you get 3x plus 3, and then plus 7. So you get 3x plus 10. Okay, so it changed x plus 1, which is a line with slope 1 going through this point here. It morphed that, or deformed it, into this other guy, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, way up here. 1, 2, 3 with a different slope. Right. So it's changing things. It's deforming pictures into other pictures. Right. Let's look at one more. F of negative x. So I'm going to put negative x now wherever I see it is the x. 3 times negative x is negative 3x plus 7. Can't combine anything else. They're not like terms, so you're kind of stuck there. Let's try another one. So here we go with the quadratic. And the important part here is to remind yourself that something like negative 2 squared is not the same thing as negative 2 squared, right? The first one is negative 2 times negative 2, which is 4. And then the second one is negative 2 times 2, which is negative 4. Okay, so it's about the base. The base in the first expression here is negative 2. The base in the second expression here is positive 2. Okay? So the exponent does not affect the negative in the second case. Okay, so you need to be able to write it appropriately so people know what the heck you're doing. So, for example, part A here, g of negative 1. Wherever I see x, I'm putting parentheses, negative 1. If you don't put those parentheses, I will mark it wrong, even if you get the right answer. I need you to be able to write so other people can understand your work. And so it's for you, too, when you're going back and looking for mistakes. Negative 1 squared is 1. Negative times negative is positive. It's 3. 11 minus 3 is 8. Let's look at another one. So here we are transforming x plus 2 into something else. So wherever I see x, I'm putting x plus 2. Okay. The first term, x plus 2 squared, you have to FOIL it. The second term, I'm distributing the negative 10. X plus 2 times x plus 2 is x squared plus 2x plus 2x is plus 4x plus 4 minus 10x. Negative 20 minus 3 is negative 23. You want to simplify these, right? You just don't want to leave them as is. Combine like terms, and we get what we get. Okay. All right, let's look at one more. This is a rational expression. So f of x is 4x cubed plus 1 all over x cubed. Okay, so first f of 2. So wherever I see the x, I'm putting in 2. Okay, so order of operations, exponents first. 2 cubed is 8. 8 downstairs. Multiplication comes next. And then finally, 33 over 8. Okay. Let's try f of negative 2. Maybe a little harder. So again, you got to put that negative 2 in the parentheses to indicate that the negative is part of the base. Okay, order of operations, negative 2 cubed is negative 8. Negative 32 plus 1, negative 8. Negative 31, all over negative 8. Negative over negative is positive. One more. So for putting in negative x, wherever I see x, so negative x cubed is still negative, so I'll have negative 4x cubed plus 1 all over negative x cubed. With negatives, you can pull those out in front. So downstairs I have a negative, I can pull that in front. Okay, but I have to be a little bit careful. Because I don't want to leave it like that either. So those two negatives floating about, that can lead to confusion. So what I'm going to do is move that negative upstairs. And the negative there will apply to the entire numerator. That's kind of what I'm getting at. So if you do move the negative out of the denominator, and remember, if you have like negative 3/5, that's equivalent to negative 3 over 5, which is equivalent to 3 over negative 5. Okay? There's 3 ways you can write it. We don't want to write negative negatives, though. So you want to avoid something that looks like this. And that's what I'm kind of trying to get out of right here. So anyways, I move the negative up into the numerator, but it has to apply to the entire numerator. So I'll have to distribute it. And then it looks real nice and presentable. Okay. Okay, let's move on. So graphing functions. In particular, they're going to want you to start comparing different functions, because you kind of build like a zoology of graphs. Sort of, they're structures, you know, they're like things that exist in the math universe, parabolas and cubics and things like that, right? You can always use point plotting, okay, at first, but eventually we'll build a zoology, and all we'll need to do is kind of move them around in the plane. Okay, so the problems are going to do these comparisons. For example, graph x squared and this other guy. Let's call it something. I don't want to call it f. Let's call it, if this button would work, that would be awesome. Okay, there we go. Call it g. And so we're going to compare x squared with x squared minus 2 and see how they're related. Okay, so I'll do a little t-table. I got my x and my y, or my f of x, and we can put everything in one table. So there's my f, and then g of x. Okay, let's just do a couple values. Let's not get carried away. Okay, so x squared negative 3 squared is 9. 0 squared is 0. 3 squared is 9. And then 9 minus 2 is 7. 0 minus 2 is negative 2. 9 minus 2 is 7. Okay, so let's plot that stuff. Going by ones. I'll do the first plot in yellow. So negative 3, 9, 0, 0. 3, 9, and it's a horseshoe type shape. It's a parabola. Okay. Like that. And then I'll do the other guy, I guess, in red. So negative 3, 7, 0, negative 2. Some extra tick marks I can draw those in. And then 3, 7, right here. Okay. And then again, it's these horseshoe kind of guys. Okay. And, you know, we're comparing them. So how does one compare the other? Well, this g of x, the one in red, is f of x, but shifted down 2. So what they're saying is kind of, you can tell it's g of x gives you all the information to graph it, so long as you know what x squared looks like. And kind of, you know, x squared is kind of simple. It's just this horseshoe with its vertex on the origin. Okay, so if you know that, to get g of x, you wouldn't have to do a table. You just take f of x and move the entire thing down, or whatever direction you need to move it in. I sort of skipped over the vertical line test, so this goes back to determining if something's a function. Okay, so we had kind of an algebraic way of doing that. If you take it and solve for y and it equals a plus or minus, it's not a function. Dealing with the arrow diagrams, it's not a function. If one x value kind of splits into two y values, okay, that stuff. When you're working with the actual graphs of the functions, then you can tell whether or not it is a function by doing the vertical line test. So most people are familiar with this. So just let me give you some examples. The first one is what we call an ellipse. It's an elongated circle. And it's used for modeling orbits of satellites and planets and stuff like that. This guy is not a function, right? Because if you drop a vertical line right here, it hits the graph in 2 places, and that means it's not a function. Most things we deal with are functions, like equations of lines, the graphs of lines are always functions, because any vertical line you draw will only hit that graph in one place. Only hits it once. Only hits it once. Okay. Parabolas are also functions. So y equals x squared, we just saw up there. For any vertical line you draw, it's only going to hit the graph in one place. Okay. So this is a function. Etc. Okay. Okay. So the last thing we want to do is kind of investigate how the domain and range are kind of related. And this is kind of another one of those deformation things. It's like when I put things into a function, it changes the number line, sort of. Okay. It changes where the, I don't know how to say it. Okay, let's just get into it. Identifying range and domain. There's this whole, there's this whole category of mathematics where all they do is study how things change, and shapes in particular. They want to study, if I take this shape and I like pretend it's clay and then I smush the heck out of it, what are the characteristics of it afterwards? How does it change? How does something change when I put it into this deformation machine? So it really is like a math science. You can study it, and it's called topology. I don't know. Anyways, let's look at some examples. Okay. So the domain is from the x-axis, and the range is kind of from the y-axis. So here we have a parabola. Let me plot the points. 3, -3, 0, -1, 4, and 1, 0. So how I usually teach it is to think of a trash compactor. So if you have a trash compactor, right, and it's smushing this thing onto the number line. So maybe here's one side of the trash compactor, here's the other side of the trash compactor, right? And it's it's smushing in like that. The residue left over by the graph is the domain. So if I smushed that thing, that graph, what would be on the x-axis after the smushing took place? And it's everything, right? So the domain in this case would be all real numbers. Or you can write an interval notation, -infinity to infinity. Okay. The range is the other direction. So if my trash compactor was smushing it onto the y-axis, so maybe these yellow things represent the two things smushing in, and they're going in this direction, and they're smushing the graph onto the y-axis, then in that case, where would the residue be? Where would the guts sort of be? It would be all this stuff, all the way up to 4. And including 4. Okay, so that closed dots, including 4. So the range in this case would be -infinity to 4, including 4. Okay. So that's the a beginner example. Let's look at one that's a little harder with open and closed dots. So open dot means it's not included. Closed dot means the point is included. So example. And what I'm talking about with transformations is kind of the function will transform an interval like this from -infinity to infinity to an interval like this. So this function, which was a parabola, so like it'll be something like -x squared. It's taken this interval, all the numbers, and it's smushed it in half. Okay, So you can kind of, as a math person, you like to study those kind of differences between the domain and range. And it's really interesting how functions transform one interval into a different kind of interval. And then certain functions will only transfer certain intervals into certain other intervals. And you can study that and identify the patterns. And it's like you're a math scientist, you know. So experiment, you know, you can make like a diary of math stuff, a journal, just like art class if you're more of a visual type person. You do a little math journal with pictures. Okay, so here's another example. And my points, I have one at -6, 1, 2, 3, 4, 5, 6, 4. -6, 4 is here. And it's an open dot, so it's not on the graph. And then I have one at -4, 0. That one's closed. And then I have another point at 0, -3. Okay. My graph looks like this. Okay, so I think in terms of trash compactors, if I smush that thing on the x-axis, there'll be kind of an open dot there, and then there'll be guts all the way up to here. So the domain is going to go from -6 to 0, including 0, because there's a closed dot at 0, -3. Then for the range, smushing everything onto the y. This will be open because this is open. Okay, and then everything's smushed all the way down to -3 where it's closed. Okay, so the range will go, and I read from the bottom up for the range, so including -3 all the way up to 1, 2, 3, 4. Open parentheses there. Okay. These problems are challenging, but I think they're a lot more interesting than 99% of the other stuff you do, because you're actually kind of thinking, again, I know I've been kind of babbling on about this, it's thinking about transforming objects, things, into other things. So you're transforming, in this case, that interval, okay, into this other interval, and it's changing the shape. You really see the shape change. If you drew those number lines, you would see how it's being compressed, right, or maybe shifted, okay? And what you do as a math person is you study that stuff, okay? Unfortunately, it's been studied for like 600 years, so there's not much that you're going to find new except beyond just having your own, I don't know, curiosity being played out. But okay, so I'll leave it there. And well, wait, let's see if there's anything unusual in Webassign that I need to look at. Oh my God. So where are we? On 1.2, maybe. So just go in there and preview this. I haven't looked at the exercises in a while. Determine if it's a function. So I don't see any repeated x values, so yes it is. Okay. No big deal there. Oh, wait. It was asking about domain. Let's go back to that one. The domain is, so for the domain, you just list all the x coordinates. So 2, 6, 5, whoops, 2, 6, 9. Excuse me. The range, you just list the y coordinates, so it's 4, 5, 9. Whoops, 5, 9. Be careful as you type. Does your relation represent a function? So it's just another one of those kind of problems. Let's go to number 7 maybe. Determine whether it's a function. I did that one in the notes. Okay, so that was, let's look at 9. Evaluating, let's try this one. Okay, so I did some like that, but I didn't do any with radicals. Okay, so this is f of r. So they're just using r instead of x. You can use any letter you want. I like to put those little hooks on my radicals so people know where they end. And then we want to figure out f of -2. Okay, so that would be square root of -2 plus 2 plus 2. -2 plus 2 is 0. Square root of 0 is 0. So that would be 0. Um, 34. So plugging that in for r, it would be 34 plus 2 is 36. Plus 2. Square root of 36 is 6. Plus 2 is 8. And then put in x minus 2. So we have f of x minus 2. That will be the square root of x minus 2 plus 2 plus 2. And that will be the square root of x plus 2. And then there's no more like terms, so we're kind of done. Root, it's not letting me do this. I have to actually hit the button. Square root of 2. No, x. X. And then arrow out of that, and plus 2. And it's simplified, so next question. Okay. So how about this guy? So this one looks kind of crazy with that absolute value thing. So we have f of x is x over absolute value x. So f of 3 is going to be 3 over absolute value of 3. Absolute value of 3 is 3. So 3 over 3 is just 1. And -3. -3 over the absolute value, -3. So -3, absolute value -3 is 3. -3 by 3 is -1. And then f of r squared. So I have r squared over absolute value r squared. Because r squared, if you square anything, it's always going to be greater than or equal to 0. Okay? So on the bottom, the absolute values are not necessary. You don't need to write them. So absolute value of r squared is just going to equal r squared. Okay? In this case. So you have r squared over r squared, that's just going to be 1. Okay, so that one's a bit weird. Graphing functions, graphing horizontal lines, graphing, evaluating functions, vertical line test. You're going to have to zoom in to get that answer. Find f of 1. So you look for where 1 is on the x-axis, and then look for the corresponding y value. So it looks like it's 1, 0. So, okay, thank you. 1, 0. Okay, that's fine. Let's zoom out a little bit. We have some story problems. The graph below shows the corruption ratings for 4 countries, A, B, C, D. The higher scores represent less corruption. Complete parts A through D. Write a set of order pairs in which countries correspond to corruption ratings. Each order pair should be in the form country and then corruption rating. Okay, so I have A. Probably want to make sure you put in capital A, comma 1.7, comma B, comma 1.2. And I need some parentheses there. Jeez, I can't read my. There we go. 2, comma C, comma 1.5, comma D, comma 1.5. What else they got? Is this a function? Yeah. Each x value. There's no repeated like a twice or anything like that. Whoops. You gotta read the whole thing though. Each element in the domain corresponds to only one element in the range. What else? Continue. Right, set for ordered pairs in which corruption ratings correspond to countries. So it's the same thing as before, except you want to switch the order. So you're going to go 1.7, comma A, comma 1.2, comma B, comma 1.5, comma C, comma 1.5, comma. You kind of see what's coming. They're going to ask if that's a function, and it won't be because 1.5 is repeated. No, some elements in the domain. No, some elements in the domain go to more than one element in the range. And then there's that. Okay, well, let's leave it at that. And so, okay, we'll see you next time.